Then question number 9. The EMF of the cell TL bar TL plus in bracket 0.001 molar, double bar Cu2 plus in bracket 0.01 molar bar Cu is 0.83 volt at 298 Kelvin. It could be increased by option number 1, increasing the concentration of TL plus ions. Option number 2, increasing the concentration of both TL plus and Cu2 plus ions. Third one, decreasing the concentration of both TL plus and Cu2 plus ions. And option number 4, increasing the concentration of Cu2 plus ions. Here in this question, an electrochemical cell formed between thallium and copper electrodes is given. Its EMF at 25 degrees centigrade is given as 0.83 volt. We need to find out the factor which can increase the EMF of the cell. Here the given electrochemical cell is this one. In this cell, this is the anode half cell and this one acts as cathode half cell. We know the reaction that occurs at anode is oxidation and that at cathode is reduction. Here at anode, thallium gets oxidized to Tl plus by releasing one electron, and at cathode, Cu2 plus get reduced to metal copper by accepting 2 electrons. Multiply the equation number 1 with 2 in order to equalize the number of electrons. By adding these two half reactions, we will get the net reaction that occurs in the electrochemical cell, which is 2Tl plus Cu2 plus gives 2Tl plus Cu. Also remember that the number of electrons involved in this reaction N is equal to 2. According to NERNST equation, E cell is equal to E0 cell minus 0.059 divided by N into log concentration of products divided by concentration of reactants. Here E cell is the EMF of the cell at any condition and E0 cell is the EMF at standard conditions. Here in this reaction, these are the reactants and these are the products. By substituting these values, the equation becomes E cell is equal to E0 cell minus 0.059 divided by 2 into log concentration of Tl plus the whole square divided by concentration of Cu2 plus. Here thallium and copper are solids, therefore their concentrations are taken as 1. If we reverse this fraction, here the sign will change and the equation becomes E cell is equal to E0 cell plus 0.059 divided by 2 into log concentration Cu2 plus divided by Tl plus the whole square. From this equation, it is clear that E cell is directly proportional to concentration of reactants and inversely proportional to concentration of products. Here Cu2 plus is a reactant and Tl plus is a product. That is, E cell is directly proportional to concentration of Cu2 plus. So E cell increases by increase in concentration of Cu2 plus ions. So here the answer is option number 4. Now question number 10. The reaction half H2 gas plus AgCl solid gives H plus aqueous plus Cl minus aqueous plus Ag solid occurs in which of the following galvanic cells? Option number 1, platinum bar H2 gas bar HCl solution double bar AgCl solid bar Ag. Second option, platinum bar H2 gas bar HCl solution double bar AgNO3 aqueous bar Ag. Option number 3, platinum bar H2 gas bar KCl solution double bar AgCl solid bar Ag. Option number 4, Ag bar AgCl solid bar KCl solution double bar AgNO3 aqueous bar Ag. In this question, a chemical reaction that occurs in an electrochemical cell is given. We need to identify the electrochemical cell. Here, this is a cell reaction given. In this reaction, hydrogen is oxidized to H plus. Therefore, it acts as anode half cell. While AgCl is reduced to Ag, therefore it acts as cathode. So the half cell reactions are: at anode, half H2 is converted into H plus plus 1 electron, while at cathode, AgCl combines with 1 electron to form Ag solid plus Cl minus. these two half cell reactions occur in the electrochemical cell, platinum bar H2 gas bar HCl solution, double bar AgCl solid bar Ag. Here this is the anode half cell and this one is the cathode half cell. Here platinum is a supporting metal for hydrogen electrode because it is a gaseous electrode. So here the answer is option number 1. Then question number 11. The standard reduction potentials at 298 Kelvin for the following half cells are given below. First one is Cr2O7 2- plus 14H plus 6 electron gives Cr3 plus 7 H2O. Electrode potential E0 is equal to 1.33 volt. Second one is Fe3 plus aqueous plus 3 electron gives Fe. E0 is equal to minus 0.04 volt. Third one is Ni2 plus aqueous plus 2 electron gives Ni. E0 is equal to minus 0.25 volt. Fourth one Ag plus 1 electron gives Ag. E0 is equal to 0.80 volt. And the last one is Au3 plus aqueous plus 3 electron gives Au. E0 is equal to 1.40 volt. Consider the given electrochemical reactions. The number of metals which will be oxidized by Cr2O7 2- in aqueous solution is dash. This is an integer type question. Here 5 different half cell reactions and their standard reduction potential values are given. We need to identify the number of metals which will be oxidized by Cr2O7 2- ion. Listen here. It is given that standard electrode potential of Fe3 plus ion is minus 0.04 volt. Na2 plus is minus 0.25 volt. Ag plus is plus 0.80 volt. And that of Au3 plus is 1.40 volt. Here the given oxidizing agent is Cr2O7. Its standard reduction potential value is 1.33 volt. That means Cr2O7 2- has higher reduction potential value than Fe3 plus, Na2 plus and Ag plus ions, and its value is lesser than that of Au3 plus. We know that the substances with higher reduction potential value undergo reduction easily, so they can act as strong oxidizing agents. Here Cr2O7 has higher reduction potential value than Fe3 plus, Na2 plus and Ag plus ions, so it can oxidize these 3 ions and it cannot oxidize Au3 plus ions. So here the answer is 3. Then question number 12. Which out of the following is a correct equation to show change in molar conductivity with respect to concentration for a weak electrolyte if the symbols carry their usual meaning? Option number 1, lambda m square into C minus K into lambda m 0 square plus K into lambda m 0 is equal to 0. Option number 2, lambda m minus lambda m 0 plus A into C raised to half is equal to 0. Option number 3, lambda m minus lambda m 0 minus A into C raised to half is equal to 0. Fourth option, lambda m square into C minus K into lambda m 0 square minus K into lambda m 0 is equal to 0. Listen here. The ionization of a weak acid HA in water can be represented as HA reversibly gives H plus A minus. Suppose the initial concentration of HA is taken as 0, then that of H plus and A minus are 0. If alpha is a degree dissociation of weak acid at equilibrium, that means degree dissociation is a fraction of moles dissociated out of 1 mole. Then the equilibrium concentration of HA becomes Ca into 1 minus alpha, and that of H plus is C alpha and A minus is also C alpha. We know the equilibrium constant of the dissociation of a weak acid Ka is equal to concentration of H plus into concentration of A minus divided by concentration of HA. Then substituting the equilibrium concentrations, Ka becomes C alpha square divided by 1 minus alpha. Cross multiplying this, the equation becomes C alpha square plus Ka into alpha minus Ka is equal to 0. We know the relationship between degree of dissociation alpha and molar conductance as alpha is equal to lambda m divided by lambda m0. Lambda m is a molar conductance at a given concentration and lambda m0 is the molar conductance at infinite dilution or zero concentration. Then substituting the value of alpha in this equation, the equation becomes C into lambda m divided by lambda m0 the whole square plus Ka into lambda m divided by lambda m0 minus Ka is equal to 0. Then multiply this equation using lambda m0 square, then it becomes C into lambda m square plus Ka into lambda m0 minus Ka into lambda m0 square is equal to 0. Rearranging this equation, it becomes lambda m square into C minus Ka into lambda m0 square plus Ka into lambda m0 is equal to 0. So here the answer is option number 1. Then question number 13. Consider the following redox reaction. MnO4 minus plus H plus H2C2O4 reversibly gives Mn2 plus H2O plus CO2. The standard reduction potentials in bracket E0 reduction are given as below. First one, E0 MnO4 bar Mn2 plus is equal to plus 1.54 volt. Second one, E0 CO2 bar H2C2O4 is equal to minus 0.49 volt. The equilibrium constant of the above reaction is given as K equilibrium is equal to 10 raised to x. Then the value of x is dash in bracket nearest integer. See, this is a redox reaction that taking place in an electrochemical cell. In this equation, the oxidation number of manganese is decreased from plus 7 to plus 2. That means it undergoes reduction, so it acts as cathode half cell in the electrochemical cell. Here in oxalic acid there are 2 carbon atoms, therefore oxidation number of 2 carbon atoms 2x is equal to plus 6. Here in carbon dioxide there is only 1 carbon atom, its oxidation number is plus 4. So for 2 carbon atoms the oxidation number is plus 8. That means the oxidation number of 2 carbon atoms increases from plus 6 to plus 8. So it undergoes oxidation. So it acts as anode half cell in the electrochemical cell. Here standard reduction potential values of both cathode and anode are given. The reduction potential of cathode is equal to 1.54 volt and that of anode is equal to minus 0.49 volt. The equilibrium constant of this reaction is given as Keq is equal to 10 raised to x. We need to find out the power of 10x. Now we can calculate the standard EMF of the cell. That is E0 cell is equal to E0 cathode minus E0 anode. Then substituting for E0 cathode and E0 anode, E0 cell becomes 2 volt. We know the relationship between standard EMF of the cell E0 cell and equilibrium constant K as E0 cell is equal to 0.059 divided by n into log K. Then E0 cell is equal to 2 and n is the number of moles of electrons involved in the balanced chemical equation, that is equal to 10. Therefore log K is equal to 20 divided by 0.059, that is equal to 338.98, which is approximately equal to 339. Therefore equilibrium constant K is equal to 10 raised to 339. So here the answer is 339. Question number 40. The potential for the given half cell at 298 Kelvin is minus dash into 10 raised to minus 2 volt. The half cell reaction is 2H plus aqueous plus 2 electron gives H2 gas. Given that H plus ion concentration is equal to 1 molar and the pressure of hydrogen gas is equal to 2 atmosphere, and also given 2.303 RT divided by F is equal to 0.06 volt and log 2 is equal to 0.3. Here H plus ion concentration and the pressure of hydrogen gas of a hydrogen electrode are given. We need to calculate the electrode potential of the half cell. Here the reduction reaction that occurs in a half cell is given as 2H plus 2 electron gives H2. Then according to NERNST equation, The electrode potential of a half cell at any condition E is equal to its standard electrode potential E0 minus 0.059 divided by N into log concentration of reduced form divided by oxidized form. Here in this reaction, the reduced form is H2 and oxidized form is H+. Then substituting electrode potential of hydrogen electrode is equal to its standard electrode potential minus 0.06. 0.059 can be written as 0.06 divided by 2 into log pressure of hydrogen divided by H plus and concentration square. Here hydrogen is a gas, therefore its pressure is taken. That is, electrode potential of hydrogen electrode is equal to standard electrode potential is 0 minus 0.06 divided by 2 into log 2 divided by 1 square. Here pressure of hydrogen is 2 and H plus and concentration is 1. Then it is equal to 0.06 divided by 2 is 0.03 into log 2. Log 2 is 0.3 approximately. Therefore it is equal to minus 0.009. This is equal to minus 0.9 into 10 raised to minus 2, which is approximately equal to minus 1 into 10 raised to minus 2. So here the answer is 1. Now question number 15. The hydrogen electrode dipped in a solution of pH is equal to 3 at 25 degrees centigrade. The potential of the electrode will be minus dash into 10 raised to minus 2 volt. Given that 2.303 RT by F is equal to 0.059 volt. Here in this question, pH of the solution in a hydrogen electrode is given. We want to calculate its electrode potential. This question is similar to question number 14. Here also a hydrogen electrode is given. Its half cell reaction is given as 2H plus 2 electron gives H2. Then according to NERNST equation, electrode potential at any condition is equal to standard electrode potential minus 0.059 divided by 2 into 2 is the number of moles of electrons into log pressure of hydrogen divided by H plus and concentration square. Standard electrode potential of hydrogen electrode is 0 minus 0.059 divided by 2 into log pressure of hydrogen is 1 divided by H plus and concentration is given as 10 raised to minus 3 the whole square. That is equal to 0.059 divided by 2 into log 1 by 10 raised to minus 6. 1 by 10 raised to minus 6 can be written as 10 raised to 6. This log 10 raised to 6 is equal to 6 log 10. By calculating, electrode potential is equal to minus 0.177 volt, that is equal to minus 17.7 into 10 raised to minus 2 volt. This 17.7 is approximately equal to 18. So here the answer is 18.